You ever wonder how your computer does, well, everything at once? You got music streaming, a dozen browser tabs open, maybe a document you're typing in, and it all just works. It feels completely seamless, right? But behind the scenes, your computer is pulling off an incredible magic trick, thousands of times a second. Today, we're going to pull back that curtain.
So here's the big puzzle. The brain of your computer, the CPU, actually has a one-track mind. It can only execute one command from one program at any single moment. So how is all this multitasking even possible? It feels like it's breaking the rules. Well, let's find out how it's done.
All right, here's what we'll cover in this explainer. We're going to start by breaking down this multitasking illusion. Then we'll get into the super clever trick that makes it all work. We'll see exactly how it's done step by step. And then, and this is the really cool part, we'll look at the new problems this solution creates, and the even smarter solutions designed to fix those problems.
Okay, first things first. Let's talk about the illusion, because that's really what it is. Your computer isn't actually doing everything at once. It's just insanely good at pretending that it is. Just imagine for a second, what if we didn't have this trick? You click to open your web browser, and that's it. Your entire computer would be completely locked up, pouring all of its energy into that one browser until you decided to close it. You couldn't even move your mouse. Every other app would just be stuck in a line, waiting its turn. That's the huge problem that needed a solution. So, how do we solve that gridlock? We solve it with this lightning-fast move. That is, and I mean this, the absolute heart of every modern operating system. It's called context switching. So what is context switching? You can think of it as the CPU's superpower to hit pause on one program, perfectly remember exactly where it was, and then instantly jump over to work on a different program. And by doing this over and over, thousands of times every second, it creates that smooth, seamless multitasking experience that we all take for granted. Now, this switch isn't just happening randomly. It's actually a really well-coordinated dance. You have the scheduler, who's like the manager, deciding which task gets to go next. Then there's the dispatcher, who's the worker that actually does the swap. But the most important piece of this whole puzzle is something called the process control block, or PCB. The best way to think of a PCB is like a super detailed bookmark for a program. It saves everything the CPU needs to know to pick that program right back up where it left off. So let's actually visualize this. How does the CPU use these bookmarks to juggle everything so flawlessly? It's really just a continuous, elegant cycle. Okay, let's walk through it. Imagine process 0 is running along, doing its thing. Then, bam, an interrupt happens. Maybe you moved your mouse or a key was pressed. Instantly, the CPU saves everything about process 0 into its special bookmark, PCB0. Then it pulls out the bookmark for another task, process 1, loads up its save state from PCB1, and now process 1 is running. The moment the next interrupt happens, the whole thing just reverses. It saves process 1 state back to its bookmark and reloads process 0 from its bookmark. It's just this constant, fluid cycle of save, load, run, save, load, run. Now, this whole quick change act is absolutely brilliant, but it's not free. It seems like every elegant solution in computing has some kind of trade-off, and context switching, well, it's no different. And that cost has a name: overhead. This is the tiny sliver of time the CPU has to spend doing the administrative work, the saving and loading of those bookmarks. During that moment, it isn't actually running your browser or playing your music, it's just getting ready to. It's basically the price the system pays for the ability to multitask in the first place. But how on earth do you even measure something that happens so ridiculously fast? Well, engineers came up with a really clever trick. They basically set up two processes to play a game of digital catch. Process 1 sends a little token over to process 2, which forces a context switch. As soon as process 2 gets it, it immediately sends it right back, forcing another switch. By timing this entire round trip with incredible precision, they can figure out how much time was spent just on the switching itself. So, what's the actual cost? Well, in this example, it's 8 microseconds. That's 8 millionths of a second. I mean, it sounds like nothing, right? And for one switch, it basically is. But your computer's doing this thousands upon thousands of times every single second. All those tiny, tiny slices of lost time, they really add up, and they create a real performance cost that operating system designers are always working to make smaller. So we've seen the trick and we've seen its cost. But this system creates a new and honestly a much more interesting problem. Remember that scheduler, the manager deciding who goes next? What happens if its decisions
aren't fair.
Let's look at a really simple priority system. Process P1 has the highest priority, so of course, it runs first. After it's done, process P3 gets to go since it has medium priority, and then you have poor process P2 with the lowest priority stuck waiting for both of the others to finish before it even gets a chance to start.
Okay, now take that basic idea and imagine it on your busy computer. Just ask yourself, what happens if there's a never-ending stream of high-priority tasks coming in one after another? What happens to our poor, low-priority process P2?
Well, the answer is a big problem called starvation. That low priority process could, in theory, just wait forever. It would be starved of CPU time. And this is a huge deal. A scheduling system that's designed to be efficient can accidentally become totally unfair, leaving some programs high and dry.
Obviously, a system where programs can just get starved isn't a good system. So, of course, another brilliant, elegant solution was invented to fix this very problem of fairness. And that solution is called aging. The idea is actually incredibly simple, but it's so smart. The longer a process is forced to wait, the higher its priority becomes. It's kind of like letting someone cut to the front of a line because you see they've been waiting patiently for hours. And this right here shows the difference perfectly. On the one side, you've got your basic priority scheduling, which runs the risk of starvation. But on the other, when you add aging to the mix, a waiting process's priorities slowly but surely climbs. This guarantees that, eventually, its number will be called. It ensures fairness in the system. To make that a little more concrete, you could have a system where, say, a waiting process gets a little priority boost every 15 minutes. It might still take a while for a really low priority task, but this system guarantees that even the most unimportant background job will, eventually, get its moment in the sun.
So you think about it. We started with this basic problem of a CPU that can only do one thing at a time. That led to the solution of context switching. But that created new problems of overhead and fairness, which in turn led to new solutions like aging. It's this incredible constant dance of problems and even smarter solutions. And every single time you smoothly switch between apps, that's what you're experiencing.